folder on Slate. I just did this today. For some reason, in the last week or two, I'm not sure exactly when it happened, but Slate actually, or D2L more precisely, changed one of their availability settings. He said, so I'll show you where it is. And basically it doesn't really, it doesn't affect us. It'll just be it was a slight glitch that a few of you pointed out. So I'll show you exactly where that is in Slate. So previously, if you went to, let me just open a chat bubble here. So if you went to the assignments folder, and this is the student view, previously what it allowed you to do is, even though the assignment had ended, so I locked the folder, you could still access the file that was attached, right? And I don't know why. In the last week or two, someone thought it would be a great idea to remove that feature. So they just did it. I didn't notice it for a while, but a few of you, I think Leander, you pointed it out in the meeting we had a couple of weeks ago, and someone else did too. We were talking about I said, do you have any questions about the quiz? And you said, I do, but where'd the quiz go? I can't see the quiz questions anymore. So basically what I did is I went through and I did a bulk edit on all of the previous things that you did. And I removed the end date, right? So the end dates have now been removed. And what that means is so two things, right? So it means you can view the attachments that I gave you, which you should be able to because they're part of the course. I don't know why there's this mentality of people to hide things, right? You've solved the problem. But so anyways, that's just a little glitch there in D2L. I did talk to Nick about it and it caught him off guard as well. And he had usually Nick has a really quick fix for these things. He had nothing for me. He said, just get rid of the end dates. That's the easiest way to do it. So that's what I did. All right. So you still have, so the files were gone for a little bit, and a couple of you sent me emails. In summary, they should be all back. Let me know if anything else is kind of weird on Slate, because they have changed the look and feel, at least on my end, of how you set assignments. So I think that was part of the overall update. So anyways, it's great when things are updated, just when you're in the middle of using them in the middle of a course, right? Nothing makes me happier than having software changed on the fly, right? But anyways, I'm ranting now a little bit. So the other thing is I posted your grade for assignment 3, right? So assignment 3, the grades should be posted. Okay, so assignment, and undoubtedly you're looking at them, right? So assignment 3 marks are posted. Assignment 3 was done generally much better than assignment number 2, right? I was very happy with a lot of the solutions I saw. I think in particular, so what was done really well was question 2, the Pratt Primality Certificate. The only sort of constant mistake that I saw was, say for that very first question, it was verify the node 173, the root node, and then you look down and you're given the prime factorization of 173 minus 1, which is 172. You actually have to check that when you're doing a certification process for a prime. You have to check that the factorization of v minus 1. So basically, this was the most common comment I put in your notes, which is check that P1 star dot 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 all the way up to star PK. In other words, the prime factorizations for V minus 1 are in fact equal to, when you take their product, are equal to V minus 1 for every node V in the tree T. Okay, so that was a very common mistake, but it only cost you 1 mark, right? So if you didn't do that, because the bulk of the work, like for those of you who did all the work, is doing that exponentiation using successive squaring, right? So you create an array for all your powers, right, of the witness to the various powers, binary powers, and then you can form your answers based on those. Okay, so that was done very well, but that was the only sort of glitch there. The question that wasn't done very well, and I think it's just because it wasn't really clear, it wasn't a clear-cut solution method for it, was question number one. So I'm going to take that one up actually. So let's start by taking up question one from A3. Okay, so for those of you who are joining late, you haven't really missed anything. We're just taking up the first question. Okay, so let's look at the very first one. The first one was so assignment three, question one, part A. Right? So in question part one, part A, it basically said, all right, suppose that g to the t is equal to 1 mod n, and that g to the t divided by the prime factors of t, pi, is not equal to 1 mod n for all the prime factors. Okay, so we're given that the two conditions for something being in order are satisfied. So in other words, g to the t n is equal to 1, and g to the t divided by p sub I mod n is not equal to 1. And then this, of course, is subject to for all pi in the prime factorization. Okay, so this is for all pi. T is equal to P1 times P2 times PI times PK. Okay, so for every prime factor in the prime factorization of T, we have that G to the T divided by that prime factor is not equal to 1, right? And basically what we had to show is that is enough. So if those two conditions are met, then we can assert that NGT is in order, okay? So given that, then we can say that NGT is an element of order. And the question basically said, show that, right? So why is it that you only have to look here and here for whether your exponents are equal to 1, right? Not equal to 1 in this case, right? Why is that sufficient? Right? The most, I don't want to say simplest, but the most sort of sensible way of showing that this is a guarantee that it's in order is a proof by contradiction. And we'll say, okay, suppose that there exists some other g to some exponent, let's call it a, such that a is less than t, and that's actually equal to 1, right? So the easiest way in my mind of showing this is proof by contradiction to say, all right, if it's not in order, that means that g to some exponent a mod n is equal to 1, where a is less than t. Right? So suppose, so this is the way you formally write it out, right? So suppose there is some g to the a equal to or congruent to 1. Let's just use let's start the congruence here because we all know what we're talking about, is equal to 1 mod n, where a is greater than 1 but less than t. Okay? So remember, the criteria for order is if you're going to say the order is t, then there can't be, t has to be minimal. So we're directly contradicting the fact that this is in order. Right? And the only way for that to happen is there must be some other value of g that's equal to 1, where there's some other exponent a where a is less than t. Okay, and obviously it has to be greater than 1, right? So if that's the case, it basically contradicts it in two ways, right? And a lot of you started off with some specific examples. That's good. I'll do the same thing here, right? I'll start with some specific numbers, okay? So for example, specific example. And the only thing we actually need to be specific about in our example is the value we pick for t, right? It's really irrelevant what we pick for the base and the modulus. Those are just window dressings on this problem, right? So for a specific example, let's say that n, g, and t is equal to 12 in order. So we can look at the array of possible values for g, right? So we can look at g to the 1, right? G squared, g cubed, all the way up to somewhere around here, which will be g to the 11 and g to the 12, okay? So, and this is all mod n, obviously, right? So if we know that ng12 is an order, that means this must be equal to 1. So this must be equal to 1, all right? And if it's an order, that means that order, there cannot be, we've checked at all the other points here, g to the t divided by pi, those cannot be equal to 1. Right? So now the thing is, we're going to have to pick, if we're going to want to prove that there could exist some other thing, we're going to have to pick some value for a. We have to pick it. And there's two ways you can pick a. The first one is a can actually be something that you get when you take t and you divide it by one of its prime factors. And that directly contradicts this guy right there, okay? So for example, let's take, so t is equal to 12, t is equal to 12, let a be equal to, let's say, let's take a is equal to 12 divided by 3, right? So a is equal to 12 divided by 3, which is equal to 4, which means that right here, g to the 4 is now going to be equal to 1, right? Well, the contradiction is this is exactly the format that's described right here. T is equal to 12. A factor of 12 is 3, right? A factor of 12 is 3, which means we've contradicted this particular. Okay. So in general, we have if a is equal to this, then this contradicts. This contradicts this guy, which is that g to the t guy mod n cannot be equal to 1 because it's equal to 1. Right? By picking a value, the choice, well, your only other choice is you pick something that a is not equal to t over some prime factor. Okay. So another thing we could do is we could say t is equal to 12, right? Let a equal to, in this case, what's something we can't, 12 divided by something. So we can pick the prime number 7, for example. Okay, so this is the only other thing we can do. It's either not in these 12 divided by prime factor results. It can be a prime number or any other number. Right? Now we have this problem where, all right, so g to the 1, g squared, g cubed, g to the 4th, this is not equal to 1 yet, right? G5, G6, and now G7, we're saying g to the 7, this is the one that's equal to 1. So we're not contradicting this guy here, but we are contradicting another thing. That sets the period at 7, which means the next time it's going to go back to 1 is not going to be at 12, right? Going on here, we have g to the 8 here, on and on and on. We're going to get to g to the 11 and g to the 12, but we are not allowed to see another one until we get to g to the 14. Okay? That implies that g to the 14 is equal to 1. And it also implies that g to the 12 cannot be equal to 1. How could it? Right? For g to the 12 to be equal to 1, we would have had to seen 1 here at g6. So then when we double it again, we can return. Okay, because don't forget what you're not seeing here is g to the 7 is some integer. G to the 8 is the same value as g to the 1. Okay, so g to the 8 is the same thing as g to the 1, which the next one would be G2, G4, G5, and this would be G6, and this would be G7 again. Okay, so that cycle repeats over and over again. So by trying to pick something that's not of the form t divided by a prime factor, we contradict the very first thing, which is g to the t mod n is equal to 1. Cannot be. So this contradicts g to the t is equal to 1 n. This one cannot be equal to 1. Cannot be equal to 1 if the period is of length 7 and this does not fall on that period. It just can't. Okay? So this is this is what I meant about starting with some, and many of you actually picked a value for G, and you picked a value for N, that's fine. You don't really need to, right? All you need to do is pick a specific value for T, right? And you'll be able to show that there's no other way, there's no other integer value you can pick for A between one, greater than one and less than T that satisfies both those conditions. One of them is always going to be flashing red, right? Saying, no, contradiction. Okay. So this actually was probably when I look at the marks on assignment number 3, it was question 1A that was the most difficult one in terms of the marks that you got back for it right off the bat, right? This one caused the most issues. After there, it was fairly smooth sailing. I'll just give you a template for B, C, and D, but before I do that, I'll just ask any questions about this particular show. We'll just call it it's not a proof, right? Proof would have to be a little bit more formal, but about this particular show or question 1A. Okay. So any questions about what you see here? You could do this more generally as well, right? In general, it would be to just omit this sort of these specific numbers. And in general, you go directly to saying, let A be equal to T divided by PI. Right? That directly contradicts G to the Ti over T over PI mod N is not equal to 1, right? You go right to the contradiction. Then you say, okay, if A is not so, I'll write it in here. This would be the general way of doing things. You wouldn't use the specific numbers 12 and 3. Say, let A be equal to T over some prime factor P of I. And that contradicts G to the T over PI, obviously. Right? The other thing you do in general is you'd say, let A be not equal to T over P. And then that will lead to your contradiction of the first thing that we stated here, which is that G to the T must be equal to the 1. It can't. This cannot be equal to 1. If you found a value of A, it's less than that. So questions? Good. Everyone seems good. Okay. Well, I'll show you what I was. So again, there was a lot of variety for question 1B as well. And question 1B. And once you see the solution for 1B, yeah, I can do 1C as well. But as soon as I do 1B, you're gonna and 1D, 1D. Just write them all on the board, Josh. Right? That's what you're really asking. Let's do 1B first. So for 1B, Q1B. This one was, what was it again? It was number of bits or something. I just gotta look at the questions here. I think I know them off by heart. Okay, show that K is always less than or equal to N, right? Why T cannot have more than N prime factors, okay? So this is how it goes for 1B, okay? So we know that T is equal to the product, right? The running product from I is equal to 1 to K, P sub I. And to give you an example of it, again, if you want to do a little specific numbers in here, you can. You don't have to use the specific numbers. But we can say, let's say that that's equal to 2 times 2 times 3 times 7 or something like that, and a whole bunch of other junk. Well, one of the things we can say is this product of primes must always be greater than or equal to the product of the primes if all these primes were 2, right? So this is always going to be greater than or equal to 2 times 2 times 2 dot 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 times 2, right? If I have K factors here, K factors, and if I have K factors here, K factors there, right? So I think we can all agree on this inequality. Right? So 2 times 2, so a string of 2's with something else greater than 2 is always going to be greater than a string of the same number of 2's. Right? So now what you do is you look at the far right-hand side and you go, well, hold on. 2 k times is just 2 to the k. Okay? And over here on this far left-hand side, we have t. So basically what we're saying is t is greater than or equal to 2 to the k, right? And now you know where we're going with this. Take log both sides, base 2. Okay, so taking log base 2 of t is greater than or equal to log base 2 to the k, right? Log to the base 2 of t, that was by definition n, right? So this is n. And over on this side, log to the base 2 of k, well, 2 to the k, that's simply just equal to k, right? Because this is equal to k times log to the base 2 of 2. You don't even need to do this. You can just say, remember what log to the base 2 is asking is, what exponent do you have to put on 2 to get the result 2 to the k? Well, I have to put the exponent of k on 2 to get to the result 2 to the k. Okay, and that was the whole point, is to show that k, so we have it posed in the form of n must be greater than or equal to k, or you can say k is less than or equal to n. Okay, so that's the that was the idea with that one, right? So that's 1b, right? So Jamie, if you're thinking 1c, it's 1c. 1c, start on the left-hand side again and say t is equal to the sum of I is equal to 1 to k of pi, right? And then what we force is we say if any of these prime factors are are unique, right? So we only have 1, 2, or 1, 3. That means that, so here we allowed the possibility that it could be all 2's. So we had 2 times 2 times 2. There was still that possibility. So that's why we had this equality, right? Equality was still there. But now, as soon as we say one of them is unique, right? At least one of them is unique. That means one of them must be different. So we have to have some integer greater than 2 in there. So for 1c, it's the same thing. T is equal to the sum of is equal to 1 to k pi. But that one is no longer greater than or equal to. It is strictly greater than. Right? This must be strictly greater than 2 to the k. Okay, so it's the exact same thing here, except in 1b, we allowed for it to be a power of 2, right? So here, I'm saying it can't be a power of 2. You have to have some unique factors involved. So again, what ends up happening is the whole thing goes down and you get n is greater than k. So ... n is greater than k, or k is less than n. Okay, so you have to have k is less than n, right? And then now that we're here for 1D, we might as well do that one too. 1D was the factorial, right? Or primorial, I should say. Right? So this was 1C. And for 1D, we're going to write, again, the same starting point. So T is equal to the sum of I is equal to 1 to k of pi. Right? So T is equal to sum k, right? And that's going to be a series of unique. So we're forcing them all to be unique so we can actually expand and make this a numerical example. Maybe 2 times 3 times 5 times, let's skip 7 just for kicks and go to 11 here, right? Times 11 times ... Well, this one must be greater than or equal to. Okay, so this series must be greater than or equal to the primorial of k. Because the primorial of k would be starting at 2 and going 2, 3, 5, 7, 11. It has to take them in the order that they appear. So once you have that, you've basically established that t is greater than or equal to the primorial of k. And don't forget what t is. T is just 2 to the n. 2 to the n is greater than or equal to the primorial of k. Okay, so if you have k factors, then you must have this criteria that the primorial of k is less than or equal to 2 to the n. Okay. Yeah, so Jamie, also good thing to point out. You weren't the only problem, not only problem. You weren't the only person who stumbled upon this issue, but the primorial because it's such a, I don't want to say obscure, but it's not a it's not like factorial, which is well used in um, combinatorics, because primorial is a little bit more sort of specific. There's sometimes different ways that it's defined, right? And many online calculators actually say, okay, you're calculating the primorial, but do you want the primorial of the first k primes, right? So do you want the product of the first k primes, which basically means as this number goes up, so 2, 3, 4, 5, 6, 7, 8, you include all of those prime numbers in your product, right? Or the other way it's defined is you can say primorial of 5, that's the product of all primes less than 5, right? So there's two different ways you can cook up a definition. I haven't really been able to find that much resolution on which one it actually is, other than what I did in the notes, which is you just define it. So I think remember in the first half of the course we were talking about primorial, and I looked at that and I thought, well, we should just define it here because there doesn't seem to be a common agreed upon definition for primorial. Okay. So the one I assumed was the one in the notes. So let's see. Curran is saying, isn't it less than? Nope, because the smallest t can be is actually the primorial of k, right? And then it can only be if this was a 7 and we stopped here, then we'd have, so for example, if we had 2 times 3 times 5 times 7, and that would be equal to the primorial of 4. Okay? Primorial of 4. But the only thing we can do to change this is to cut out a 2 and make it start at 3, right? So any modifications to these prime numbers means that they must, remember, they're all unique. So if they're all going to be unique, my only choice is to introduce a larger prime. So that's 2 times 3 times 5 times 11. Now that's greater than primorial of 4. Okay, so it is that way. Right. T is always going to be greater. The smallest number you can get from taking a product of primes is the primorial. If they're all unique, right? If they're not all unique, then you can have all 2's, right? But we said they all had to be unique. Okay, good. So hopefully that sets you up with an idea of, that's what I was looking for question number 1. I like taking these types of questions up on the whiteboard, also because this isn't the only way to solve them. And when I post an answer key to stuff like this, it makes you think, well, how was I supposed to know to solve it that way, right? There wasn't. Many of you solved these questions in very different ways, and some of you got full marks for them, right? So you didn't have, this is just the easiest way that I know of to do it, right? So when I thought of what's the simplest way to actually show those relationships, this is what I came up with, right? But many of you came up with alternate ways, okay? The only other thing, I realize we're running out of time here. The only other thing I wanted to point out was that the optional math induction question, right? So I noticed that no one in this group, in this class, took it, right? So everyone just did the primality certificate verify, the primality certificate construct, right? No one did that induction question, right? So I'm going to grade, I haven't graded the other section yet. We'll see if everyone in the other section also avoids the math induction question. And just to let you know, this is something that I often do. When a math induction question or any question is avoided by everyone, it doesn't go away. It sits around and it comes back for a return cameo appearance on the next assignment. And there was an instance where it was 4 or 5 years ago, I think it was, where an induction question survived a couple of assignments. No one took it. And then just for fun, I put it on the test, right? So now your test, you're going to have a choice of questions, right? So we'll see if anyone takes this induction question and solves it, right? But I do like to make them survive until someone actually tries to solve it, okay? And Jamie says induction is no fun. That's why I made it an option, right? It's still going to be an option. It's not like I'm going to force it. It's not, right? Even if it does make another appearance on the test, you have a choice to choose it or not. Right? Yeah, April Fools. Yeah, that's my little April Fool's joke. Probably the worst April Fool's joke you've ever heard. Okay, So you might see the induction question return as an optional thing on assignment 4 is what I'm saying. But I have a lot of stuff already ready to go for assignment number 4, right? So assignment number 4 is going to be a decrypt, classic crypto assignment, decrypt some stuff, right? And I will try to have that available sooner rather than later because we're running out of time very fast, right? And I don't want to have assignment number 4 due when you have all your other course assignments due in the last week. So I'll try to get that out sooner rather than later. Right? Good. Okay, so that's all I wanted to talk about in the meeting today. Just talk a little bit about assignment number 3. There's still some meetings today, which actually should have started a minute ago. So what I'll do is those of you, so Kiefer, Jessica, Clinton, you're the first 3. So I'll see you in, let's say, about 5 minutes, right? So we may be running 5 minutes late if you got your meeting today. Other than that, for the rest of you, have a great, Easter weekend. We have our next class will be Tuesday next week, and we'll be doing the second last crypto system ever, right? So Regev, the Regev crypto system we'll be looking at, which uses the learning with errors problem. Second last one, and then a week later we'll do the very last crypto system, right?
Excuse me.
Yep.
Yeah, what did I miss?
What did you miss? I just took up the questions from assignment 1, right? Just actually one question, and I'll put that on the whiteboard for you, Christopher.
Oh, you mean assignment 3?
Sorry, yeah, assignment 3. Question 1, assignment 3. Yeah.
Yep.
But I'll have all those things on the whiteboard for you as well.
Would you still accept the quiz I just sent you?
Oh yeah. You emailed it to me, right?
Yeah, the learning with errors, it looks very confusing, even with the solutions you gave me. I just rush and try the best I can.
Yeah, okay. Okay, tell you what, Chris, let's take this. So just because we have everyone here, we can always drop by the personal meeting room that I have at around 2:00, and I'll let you in then. If you don't have no, you did your meeting last class, okay? So drop by the personal meeting room at around 2, and we can continue this conversation, okay?
I'll do it in my next one.
Okay, that's fine. We can take it up then too. Sounds good. All right. Okay, everyone, have a good weekend. We'll see you later. Those of you who have your meetings, we'll see you today. Okay? Take care. Bye-bye.